All right, OChem, welcome to Basis Online. All right, we'll see how things go. Today's lesson number one, will be a review on determining R and S configuration in molecules. So you guys need to remember that molecules can have a stereocenter in them. Let me get this going. Can have a stereocenter in them in situations where there are four different chemical groups or atoms. Chemical groups or atoms, around a central carbon. All right. Now, if that's the case, so you have a central atom that has four distinct chemical groups about it, let me go and just get our first molecule. So we're going to have a central carbon, and then there's going to be a hydrogen here. We'll have a chlorine extending out like this. Obviously, I assume that you guys know this kind of notation by now. And on this bond, we're going to have a hydroxyl group, and then here I put a sulfhydryl group. So this particular molecule has a stereocenter because we've got four completely distinct chemical groups around it. And what are the consequences of that? So what this means is that this molecule is going to have two stereoisomers. All right, and the two stereoisomers are going to be what we call enantiomers. Now, this is a hugely important thing in organic chemistry because when you have enantiomers, what that means in reality is that even though, like if we look closer at this molecule over here, even though both of the stereoisomers are going to have exactly the same connectivity, if we break and we switch two of these chemical groups in terms of their placement, this creates the opposite stereoisomer, and you have a situation where you now have two molecules that have a right-handed and a left-handed version, which means that their three-dimensional shape is distinct. And if we were to put them, take one of them and place them in a mirror, they would have what are called non-superimposable mirror images. And I'm going to come back to that concept in a minute. Because we have done this, what I'm going to do right now is just very quickly remind you what you have to do in order to see or define the left and right-handed version. So, and that's going to be basically determining the R and S configuration, how we do that. Now, the R and S configuration in reality don't really have like a chemical meaning because they use optical spectroscopy to look at these things and actually see, you know, the two different molecules to actually be able to visualize them in space. I mean, and if you need to do this yourself, the one metaphor that I can think of is to look at your left and right hand. They're identical in terms of the connectivity between the fingers and the main body of the palm of your hand, but if you try to overlap them, if you try to overlap your hands, it can't be done. All right. If you stand in front of a mirror and you hold up your left or right hand facing the mirror, then you're going the image that is being projected back to you is the non-superimposable mirror image of the hand that you're holding up. So how do we figure out the R and the S configuration? So the first thing you're going to do is take and rewrite the molecule so that the lowest priority atom is faced directly into the plane of the board. Now, how do we decide on the prioritization? So with the simplest molecules, like the one that we're looking at, they're basically where the connectivity is going directly to a singular atom. In the case of the hydroxyl here, yeah, there's two atoms, but the connectivity between the carbon is going directly to an oxygen. And for the sulfhydryl, it's a similar situation. The carbon is bonded directly to the S, and then the S to the H. So what we're going to do is compare the priority of each of these initial atoms, the ones that are bonded directly to the central carbon. And the way that we're going to determine that, all right, so one thing, all right, let me just outline this. So we're going to prioritize, and we're going to do that by atomic number to start with. By atomic number. So in this case, the Cl is 17, the S is 16, the oxygen is 8, and hydrogen is 1. So I'm going to take the molecule to start with, and I'm going to rotate it so that the hydrogen is back. All right, so I'm going to take it and twist it a little bit, or just kind of turn it. So here's my central carbon. We can't see the hydrogen now because we're literally looking down a tangent here directly at the carbon. The Cl, I'm going to keep it out of the plane of the board. So you can kind of like visualize which way I rotated this a little bit. The hydroxyl group is going to come out a little bit, and then the sulfhydryl group is going to be here. So if I put my Cl in, the OH, and then the sulfhydryl back. Now, Cl is 17, so it gets a, you know what, let me change the color of this thing. So it's going to get a 1, and I'm using 1 as the top priority. And then the sulfhydryl is going to be next, so we're giving it a 2. The hydroxyl, the O, is last, so that's a 3. And then what we do is we scroll a line, starting just literally just following the counting. And you can see that when we do that, that my line went in a directional sense in counterclockwise direction. So this molecule is the S configuration. All right, now, whereas the clockwise is going to be R. So now let's take a look at this, the mirror image argument. So down here I'm going to just draw a dotted line, and this represents a mirror. All right, and then I'm going to take our molecule and I'm going to rotate it to the left a little bit. And so here is so I'm taking this molecule here, just to be really clear. All right, and the H is now going to be straight back. And I don't know if you guys have your model kits. It's definitely easier to follow me if you've actually got models of these things to start with. So when we rotate, in other words, when we bring this thing around, so we bring the hydrogen around this way, this is going to go back. This is going to come out a little bit more, and this is going to stay pointed down. So what we're going to have is going to be something that's going to look like this. All right, now this is my mirror. So the molecule on the other side is going to look like this. The H is going to be like that. All right, and then we're going to have the OH is going to be here. My Cl is here, and the SH is here. Now, let's take a look at the new molecule. So I'm going to circle this. We'll do the same thing to the other one so you can see that I didn't screw up, and I guess I'll find out myself if I screwed up or not. So we're going to pull this over here, and what I'm going to do is I'm going to go ahead and rotate it. I'm going to do everything at once. So here's my central atom, carbon. We can't see the H because it's literally back in the plane of the board. Here's my Cl. Okay, here's the OH. And, whoops. And here is the sulfhydryl group. All right, and again, this is priority number 1. This is priority number 2. And this is priority number 3. So now when we do the scrolling, you can see that we went clockwise. This is the R configuration. So this is a non-superimposable mirror image. All right, now let's just double check this other one to prove that when I rotated it I didn't screw anything up. So I'm going to grab this, and this is going to get dirty, but who cares? All right, here we go. Boom. So I'm going to move again. I'm going to rotate so the carbon is back. All right, and as I rotate it back, so I'm going to rotate it this way. Let me go in red. So I'm going to rotate the molecule that way. So this dude is going to come this way. This is going to come this way. And we'll rotate on the SH like it's an axis. All right? So that means that the Cl has to be here. And the OH has to be here. And the sulfhydryl, we rotated on it like it was a peg leg or something. All right? So it's here. Now, this is number 1, this is number 2, and this is number 3. So I go ahead and scroll around, and you can see clearly that it's counterclockwise. So this is the S. So going from this guy here to this thing here in my mirror, I didn't change anything. All right, and then the mirror image was drawn correctly. So you can see that these two molecules are in fact enantiomers. All right, and this concludes the video. This is lesson 1 in determining R and S configuration in molecules. In the next lesson, we'll look at molecules that have stereocenters that have more complex external atoms. All right, so good luck, and we will see you next time.